Hello and welcome to this Aviation Week video interview. I'm Graham Warwick, Executive Editor for Technology. Our guest today is George Bye. George is founder, CEO and chairman of electric aircraft company By Aerospace. He's a former US Air Force fighter pilot and an air transport rated pilot today. George designed the Javelin jet trainer, if you could think back that far. But he was also behind the Sunflyer prototype, early prototype all-electric aircraft, and the solar electric Silent Falcon. So he's been in the electric aircraft business for a while. Fast forward to today, and By Aerospace is developing the two-seat eFlyer 2, which is an all-electric training aircraft. And it promises to dramatically reduce the cost of training new pilots, as well as reducing the noise and eliminating the emissions from those training flights, which will be very popular for the people around the airport where those people are being trained. But By is also aiming to be the first to actually get FAA Part 23 type certification for electric aircraft, which would be a major, major milestone. So George, welcome. Thank you for joining us.
Thank you so much.
As we've noted here, you've worked on electric aircraft before. So what and unmanned aircraft. So what made you decide that the technology was ready for manned aircraft? What did you have to see from the technology to think that you could go forward with this?
Yeah, that's a great question. Going back some years, many years actually, to the early days of EVs, there were the questions about batteries and range, their energy density, motor capabilities. All of those things, of course, were colliding to challenge the emerging EV ground vehicles. And certainly all of those same criteria impact the ability to create airplanes that solve problems. And I think what's important beyond research, our great friends at NASA and others that do tremendous research, the practical application of these new technologies is to solve a problem. And early on, 10 years ago, we developed a solar electric UAV called the Silent Falcon. It's in production today, by the way, and doing great work as a 14-foot wingspan, 15-foot wingspan solar electric drone. Very, very cool. I'm immensely proud to have created and designed, developed, and of course now, like I said, in production by our former subsidiary, the great people at Silent Falcon. But the point is, at that scale, in the early days, the energy density of the battery, the collection of solar energy from the sunshine, and the electric motor allowed slower flight, long glider type wing, high aspect ratio, high aero efficiency to take advantage of the in effect extremely low cost of using electricity as an energy source. And of course, many drones, many UAVs are operated remotely or somewhat remotely. And so the challenge of fuel access and availability, as opposed to electricity being a little bit easier to access, and the energy cost being so much less, was the original concept at that scale to bring electric to the market in this drone configuration. Now, what's happened since then, again, the trajectory of energy density of batteries, in particular, the configuration of electric motors going from industrial applications to aerospace applications, and the kilowatts per kilogram, the ability to create energy into torque to thrust, has continued to improve just like battery energy density has. So to your point, we progressed into manned scale prototypes, a couple of different ones, as you point out. And now we're at the ready to pivot into not just prototypes and research, but the full criteria under that 14 CFR 23, the new Amendment 64, which allows for the very first time on a fully certified Part 23 aircraft, the ability to have electric propulsion. A very, very great milestone, as you point out, and literally the eFlyer 2 is the first entrance into this new paradigm.
So we're talking about the eFlyer 2. So where are you in that development? And clearly from what you say, you know, it's not just a case of putting some batteries in an airplane and sticking an electric motor on the nose. In order to get this system, this aircraft system to work, you've got to do more than that. So the eFlyer 2 is clearly, you know, not your run-of-the-mill airplane in its own right. So,
Graham, I couldn't agree more. And we've got great friends that are looking at various other business models with electric motors and things, as we all know. Great people, pioneers in their own right. However, when you look at an initial entry into electric aircraft, it's far more than just batteries, as you point out, as important as they are. Understanding the energy density, the weight and balance, the configuration of the airplane itself, the requirements for battery charging, battery cooling, system balancing, and of course the ability to apply that energy through the computer system, the battery management system, to the motor computer system, it's an inverter controller, and then being able to practically apply that to an actual mission. The utility of the aircraft is not a trivial exercise. Very sophisticated. Simple in the overall explanation in terms of here's energy storage and here's its application to create torque, but the reality of the technology and the process is sophisticated. What's interesting though is again, kind of coming back to our earlier point about electric aircraft design. The motor characteristics, the battery characteristics, and the cabin, the design around the cabin and the purpose of the eFlyer 2 in particular as a trainer, is of course to create a training system, a training environment for instructor and student. So 46-inch wide cabin, modern avionics, instrumentation, the great lookout, the ability to have practical, robust landing gear. A lot of us remember as young pilots, you know, we spent a lot of time doing touch and goes, and it's a workhorse airplane. I mean, the bottom line is you spend a lot of time doing touch and goes. So robust landing gear, slow flight characteristics, all those things are so important. Electric for the sake of electric is overwhelmingly important, disruptive even, especially if you talk about the operating cost. But you have to have a practical airplane and platform from which to do this mission. But interestingly, and I think this is surprising to many as we talk about this, is the propulsive system efficiency of electric. The motor, depending on which motor you're talking about, 17 to 20 inches in diameter and 4, 5, maybe 6 inches deep. And of course at 95, 96% efficient, there is almost I'll say this, very limited cooling requirements.
right.
The excess energy not used to create torque, of course, is heat. And it turns out there's very little of it when you're that efficient. So what happens is, on a purpose-built electric airplane, all of those features that I was just talking about, from cabin to airfoil, structures, the layout of the batteries and the motor, the various computers, the BMS we call it, the battery management system, the controller, inverter controller, all of those are laid out in an advantageous way, so that literally the eFlyer 2 as an airplane design has twice the aero efficiency of the Cessna that we're replacing. Cessna, Piper, Diamond, etc. We don't have the flat plate area in the front for drag. We literally have an L over D of over 20 as opposed to an L over D of 10, 9.6 to 10, 11, 12, depending on which trainer you're referencing. But the internal combustion engine requires a great deal of cooling surface area. The first third of the propeller in a conventional airplane is used to allow cooling air to come across those cylinders. So what a wonderful thing to have a very sleek, slim forward fuselage area, aerodynamics, and the overall layout to take maximum advantage of the aero efficiency, propulsive efficiency of an electric aircraft.
That's amazing. So when will you, I mean, where are you? I mean, when will you fly the conforming vehicle, and are you still hoping for next year to get certification, or has COVID pushed you back a bit? And
yeah,
and also when you talk about certification, you know, one of the things here is you've also got to put it out into service. So I mean, you've got to, presumably there's a lot of work that you've got to do with the flight standards folks to get everything in place so that when you deliver these, they can immediately go into training service.
Yeah, Graham, for those of this that the whole idea of grit, determination, persistence, you put that together in that same sentence with when you talk about the FAA, right? I mean, that's we love our friends of the FAA. They are us, right? They are us. All of them come out of this industry that we love. And their primary reason for existence is safety. And we want to make sure that this is the opportunity to create the world's safest general aviation airplane ever. So we're in complete alignment. On the other hand, this hasn't been done before. Amendment 64 is a structural outline of a vision of what certification can be, maybe even should be, but it's not filled in yet. And of course, the previous amendments have lots of experience behind them, lots of paperwork behind them, and the designated engineering representatives and the FAA themselves, of course, can rely upon previous technical work to help move through a traditional conventional certification that doesn't exist for electric. So literally, we are working together with our friends at the FAA almost daily to help define what certification looks like for an electric airplane. That has never literally been done before. The ability to reference materials doesn't exist, so we're creating them. Being a pioneer is a wonderful thing. Being a pioneer is, again, back to that grit, courage, determination. This is not a light sport aircraft. It's not company qualification and agreement, but rather it is the complete Part 23 process, which is a true deep partnership with the FAA on every level.
So, and that includes being able to deliver it and be flown for training missions as soon as it gets delivered.
Yeah, they're to your point, the process of certification, of course, isn't just it's a milestone. It's a process. It's the ongoing quality assurance, the ongoing airworthiness, the producibility, repeatability, the operation in the field with the customer. All of that's part of the continuum of FAA certification under Part 23, and of course that is the fundamental basis for problem solving, for creating a business tool, in this case an airplane, that brings with it to the flight schools, the fleets, of course starting with training with eFlyer 2 and eFlyer 4 we'll talk about in a minute, but it starts with this fundamental baseline that we all understand in this industry literally for decades, how we behave as a manufacturer with an aircraft to the customer, and the operating manuals, the maintenance, the support, all of this all works together in a symphony to in this case, bring new pilots through and prepare them for their future in the aviation industry.
Now, obviously, the process that you're going through with eFlyer 2 is going to be fundamental to your next step, which is you've talked about the eFlyer 4. So is there more technology development that you need to see before you can go up that size? And also, you've talked about bigger airplanes, you've talked about a 6-seat, you've talked about a twin. Is there some sort of a roadmap for technology you need to see before you can make those steps?
So going from the 2-seat to the 4-seat literally is a matter of scale. And happily, again, as we know, the drag rise with increasing velocity within reason in a single engine general aviation aircraft, kind of that 130 to 160, 170 knot range is manageable with the existing battery cell energy density, doubling roughly the battery pack size. That's 75 kilowatt hours in the eFlyer 2 and roughly double that in the eFlyer 4, the 4-seater. So it turns out with careful care and attention to details, but it turns out to scale from a 2-seat to a 4-seater with the same FAA certification criteria, roughly the same structural system, aerodynamic system. Generally, the aircraft layout remains the same. It's kind of a stretch. I don't mean to be overly simplistic, but in effect, it's a stretch. And of course, there's a significant gross weight increase, 12 or 1,300 pound gross weight increase. So it's a kind of like going from a Cessna 172 to an Cessna 182 or a 206. So the airplane has generally the same appearance. It's very sleek. It's very cool. However, at least going from eFlyer 2 to the eFlyer 4, the physics close, the mathematics close, structure, airfoils, layout, all can share in that common DNA that we've developed for the eFlyer 2.
But if you go beyond that, I mean, to some of these bigger airplanes you've hinted at, I mean, you need to see technology develop to go that way, do you?
So what happens? We have what's called the eFlyer X, and then there's a twin that we call the Envoy that comes after that. So it's as we go higher and faster. The eFlyer X is a 6-seater. So you go from 2, 4, and 6.
Right.
And then the Envoy 9-seater. You go higher and you go faster. Now, the higher part, that's kind of fun. Our developmental prototype, we've been flying for a couple of years now, as you know. You know what's crazy? We have the same rate of climb at 9,000 feet as we do at sea level. Electricity does not consume, there's no combustion. Yeah. So electrons to torque is the same at sea level as it is at 9,000 feet. With other technical considerations, and you do have to watch the effect of the amount of air and proximity to high voltage systems. So it's not just, oh, let's go climb high, but the fundamental behavior of electric is indifferent to altitude. So it does turn out that a lightly pressurized 6-seat airplane at 25,000 feet with some attention to details, but the bottom line is electric loves to fly high, and the calibrated airspeed to true airspeed benefits are fully realized. What a wonderful thing, and the ability to get there, the climb rate all the way up is not diminished as you get up into the you know, the low to high teens and even the low 20s. So there's great promise for the eFlyer X, the 6-seater, lightly pressurized, retractable. However, most people who buy an airplane of that type like to have the longer range,
right,
the greater distance. So while the business case for the eFlyer 6 closes today, the desire for a higher energy density battery would bring even a greater benefit to the eFlyer X, the 6-seater at altitude, because that customer, the customer that likes the light twin or the, you know, the high-end single, higher speed, higher altitude, is generally looking for a little bit more range.
right.
So energy density is a consideration. It may impact the formal launch of the eFlyer X program. However, the business case does close, and likewise as we go on to a twin configuration, a 9-seater, a twin, the technology available today or in the very near term would close the business case. It'd be a shorter range, higher altitude, even yet again, probably about you know, the higher end of where King Airs and the other turboprops fly. But range considerations and energy density are the ability to make that an even more useful.
Right.
So that's where the relationship with Oxys comes in, with the lithium sulfur, 500 watt-hours per kilogram energy density. Lithium sulfur is a great technology. It's a great battery cell, but it's not quite ready for certification. It's not quite ready to be applied into a formal certification program just quite yet. So our relationship with Oxys and the ability to kind of apply that to the X, certainly to apply it to the 9-seater, to the Envoy, is dependent upon a little bit more R&D.
Right.
And we're working actively with Oxys and some other great friends that we'll be talking about here in the next few weeks about creating prototype large battery packs using these advanced cells. And again, looking at some of the challenges for lithium sulfur, of course, is the C rating. Some of the challenges for lithium sulfur are cycle life, the practical application of these advanced cells, and a great partner with Oxys is the roadmap to help enable those higher performance aircraft.
You know, you mentioned there about recharging rate. Presumably, again, if you're talking about a longer range vehicle, the aircraft's not going to be turning around and coming back straight away. You might get a little bit more time on the ground with a longer range airplane touring, or you know, a longer range than you would do with a trainer, which is going to turn around time and time again. So maybe there's some.
Yeah, so that's a great point, Graham. A lot of people wonder about, well, what is this whole idea of recharging time? And of course, in the EV world, we've seen recharging times dramatically drop. The level 2 chargers are being replaced by level 3 chargers, and even level 3 chargers plus. And as the lithium ion battery cell technology continues to improve, this whole idea of C rating, or the ability to accept charge or provide energy to the electric motor, continues to improve as well. And so that directly affects not just the behavior in the air as applied to eFlyer 2, 4, and on, but more importantly, for the high ops tempo flight schools and air taxi operators, is how long does it take to recharge? What's my ops tempo? What's my ops tempo? And a 1C or 1.3 or 1.5C energy cell can accept energy, in the case of the eFlyer 2, for that 1 or 1.3 hour flight time in about 20 minutes. So the eFlyer 2 ops tempo is as good or equivalent to a conventional aircraft refueling, and we're very pleased to announce to our customers and work together with them that the ops tempo, the rhythm of flight training, the turn time from one event, one sortie to the next, is well within, in fact, even improved in some cases, compared to the ops tempo that they're currently using with conventional aircraft.
All right. And is lithium sulfur your leading candidate at the moment? There are always new battery chemistries around. We're talking about lithium metal, solid electrolyte. It's hard to get, and we're now hearing more and more talk about fuel cells in recent months. I mean, do you think at the moment the lithium sulfur is the most promising?
Well, the lithium ion trajectory has chemistry limitations eventually. There will continue to be, and you've seen announcements, I'm sure, of lithium ion cell technology advances. And, we're at 260 to 270 watt hours per kilogram right now. There's plenty of people with fundamental in the lab and even research ready cells that are 300 plus energy density. Of course, the question that we have is its certifiability. And again, you may get a higher energy density, but can you recharge it? What's the cycle life? And of course, the cost per cell as it's applied to various applications. So we are delighted to see these advances and work together with many, many different providers, but our current cell provider and the certifiability, repeatability, cost, C rating, temperature, cycle life, all impact, of course, the practical application on the eFlyer 2 and the 4. Lithium sulfur has a greater trajectory. The chemistry of lithium sulfur offers a longer roadmap to higher energy densities and the ability to hold that energy. The question is to get the configuration so that the charge and discharge, the cycle life.
Yeah, sorry about that. My printer just went off in the background.
We're not picking a winner, but in the near term, the near-term certifiability of lithium sulfur holds great promise. And Oxys is, we think, the world leader, and they understand this practical application. So we've partnered with them, I think, with great hope, great promise, but quite frankly, great engineering. It's not a hope, it's a pathway. And again, as we make ready for eFlyer X and Envoy, that technology is appropriately underwriting and supporting that emerging aircraft capability.
So just to wrap up here, you've been you're a pioneer of electric aviation, but since you've sort of entered this, back with the Sunflyer and we've seen the electric aircraft market just explode in different areas. We have the electric light aircraft, but we also have the electric VTOLs. We're starting to see electric STOL designs, etc. I mean, that must be sort of gratifying for you to see that you kind of that you backed a horse with a lot of energy in it going forward. I mean, how far do you think this can go? I mean, is electric aviation the future, or will it always be how far do you think you can go with electric aviation?
Yeah, that's a great question, Graham. Just a few years ago, and in fact, you may have been in the audience. I would give talks about the future of aviation and in particular electric aviation, and somebody in the audience would ask how long's the extension cord. You know, and everybody would laugh, and you know, skeptics everywhere. Batteries will never evolve. You know, we'll never get there. It won't ever be practical. I'm immensely satisfied to see so many great friends in the industry talk about the future with electric. And of course, there's many programs, as you've talked about, and others on your team are editorializing and reporting on these various programs, many of which I hope will in fact succeed. Many of them have deep challenges, technical challenges. You know, the whole, again, kind of going back to the physics of flying, there's just mathematics that make some of those things very, very challenging, very difficult to actually achieve. Interesting in theory, interesting in concept, but very, very hard to do. So back to that, you know, the theme of the conversation: grit, persistence, etc. But we see, to answer your question about the future, we do see electric as a profoundly important solution. Maybe not solely, but in conjunction with other technologies, electric is going to have a big role to play. And again, back to the beginning of our conversation, it's so beneficial to cost. Operating costs are how we live in the business, in the aviation business. Operating costs, we either live or we don't, by the cost of fuel, the cost of maintenance. As older aircraft require more maintenance, oh my goodness, it's such a challenge. And the cost of fuel, as we all know, can be devastating. The ability to bring costs down, operating cost comparison from an eFlyer 2 to a traditional conventional trainer is 5-fold less, 1/5 the operating cost. As we go to the 4, the X, and the Envoy, that same paradigm of benefit, operating cost benefit, is profound. It's disruptive. I can't even imagine an electric fleet coexisting with a conventional fleet on a given airport or region performing the same function. Clearly, there's difference in function. So that benefit, as it's realized, will make its way through at least the single engine fleet utilities, light twin, and then again, we need timeline here. As we get out 5 and 10 years, we need timeline for some of these next generation technologies to kind of allow us to move farther into higher speed, higher altitude, and larger volume or payload aircraft. And some of those will be enabled by other devices to carry electrons. And as you have mentioned, it may be a hydrogen fuel cell, for example, or other kinds of fuel cells. There are a number of technologies that people are kind of imagining, concepts that create the ability for electric motors to go on higher speed aircraft. Hybrid systems, probably not as often as they're discussed, but a very thoughtful application of a hybrid system can indeed provide incremental benefits that are worth the near-term investment to a longer-term fleet use and the ability to pass along those benefits in a business case. Some of the hybrid applications I'm a little question mark on, because you have just as much investment from an R&D perspective and certification perspective as you would if you were all electric. So there again, the cost benefit and application trade-offs have to be kind of thoughtfully considered. But the future is electric, and a lot of it will at least use electric because of its great benefits. It will scale 5, 10, and 20 years out. Some of these other technologies will continue to mature and be certifiable. I'm bullish on the future. I really truly am. Great people. It's a team. It's an industry, and we can do this together.
Well, thank you, George, and thank you to you and your company for setting being a leading light in this and showing what can be done. And the best of luck with getting the eFlyer 2 certified and getting it out into training use and whatever follows, the things that follow. So thank you very much for talking today. It's great to see you again. And so we're wrapping up our interview today with George Bye, the founder, CEO and chairman of electric aircraft developer By Aerospace. Thank you very much, people.